Well, now that we've figured out how to do Euler's method in Maple, it's a powerful tool for being able to approximate a solution value. We need to kind of figure out what those types of types of error might be that are going to affect our approximations, affect our estimates. So it really boils down to a concept that we learned way back in Calc 1, concave up and concave down, or sometimes concave and convex are the different ways that people have referred to them. So the value of the second derivative, as we learn in Calc 1, tells us about the concavity of the function. So really, what we want to ask is, what happens for a function that is concave up? A concave up is second derivative is greater than 0. That's what a concave up means, and of course, concave down is the opposite. Second derivative is less than 0. But what that means in terms of a graph, if you imagine we're looking at a function y equals f of x versus x, we'd be able to tell what's happening to our curve by taking a look at this. And so I'm going to draw my axes for both of these here. And so if you imagine starting at some initial condition, and the actual function goes something like this, there's our start, and there's our end points, and this is the actual curve, right, the actual solution. Our approximation, because we're always taking a step and following kind of a straight line, it's always going to be out here. Approximation is always going to look something like that. So this is always going to be approximating a little bit below. If it's concave up, we're going to be approximating a little bit below where the actual value is. So the type of estimate that we expect is always going to be an underestimate for the y value, for the f of x value. I don't even want to say f of x, I just want to say y value, because we're talking in terms of x and y here. And likewise, but in the opposite direction, if you imagine a concave down curve, that means you might be starting somewhere like here, and the curve is going like this. And this could be your start, and this could be your end, your stop. Call it end, I guess. And this is the actual curve. And so your approximation along the way, because you're going to be taking a step away and then following the path, and you're always going to be kind of going a little bit outside. And so your approximation, because it's concave down, is always going to be a little bit of an overestimate for the y value. Right? Because this is your error right here. That's the error that you're off by, just by virtue of the fact that there's the curve itself is not a straight line. There's a concavity to it, right? So the way I like to think of it, down at the bottom of this page, I'll add a couple of notes here. Predictions always hug the outside edge of a curve, if you want to think of it this way. So if your curve is curving upward, it's going to be below. It's the approximation is always going to hug the outside edge, right? And if we analyze the differential equation for concavity, we can actually know what kind of error we expect. So we analyze the concavity of the solution by looking at the derivative of the derivative to know what error to expect. Right? We know what error to expect just by taking a look at the derivative of the derivative. And so as an example on the top of the next page, we'll take a look at this. We're going to check y double prime in the vicinity of the starting point. Now, just a reminder, I'm using for this the previous problem, which, if you recall, the previous problem was y prime equals t squared minus y squared, and our initial condition was y of 0 equals 1. Right? So we're going to look in the vicinity of that starting point and say, what's going on there? So if we start with dy dt equals t squared minus y squared in the vicinity of y of 0 equals 1, then we take the second derivative, and we basically take the derivative of the derivative, and we get y double prime equals, take the derivative with respect to time, this becomes 2t minus 2y using the chain rule times dy dt. And so taking the derivative of this whole thing gives us this. And this is our second derivative. This is our d2y dt squared. So that means it's really 2 times t minus 2 times y times the derivative. And this right here, this is the first derivative, which is all this stuff right here. That's dy dt. So I can do a substitution in for that. And I can just substitute t squared minus y squared right there. Right? That is the equivalent of dy dt. And so in the vicinity of t equals 0 and y equals 1, I can estimate what's going on. So off to the side I say, so near t equals 0 and y equals 1, we can say y double prime is roughly equal to 2 times t, which is 0, minus 2 times y, which is 1, I'm just getting this from over here, times t squared, which is 0 squared, minus 1 squared. And so 0 minus 2 times, this is negative 1, so minus 2 times negative 1 is positive 2, so y double prime is approximately equal to 2, which is definitely greater than 0. Greater than 0 second derivative means our solution curve, we expect it to be concave up. We expect y of t's, that curve, to be concave up.